Okay. I made some mistakes. I'm just gonna start this explanation over again. Correction, a couple of things. We want to graph this function. First thing that we do when we graph any function, we find the y-intercept, which occurs when x equals 0, and the x-intercept when y equals 0. We want to write that out to reinforce it. We want to write this. We want to write this to keep reminding ourselves of what we do. Now, if we let x equal 0, you see what we get. We plug in 0, and everybody can do that. We're going to get negative positive 5. The x-intercept occurs when y equals 0. So we set y equals 0. We set this thing equal to 0, and we get this equation. Now, we can shortcut it because the only way there's going to be 0 is the numerator 0, but there's still advantage in solving this equation. To solve this equation, we're going to multiply both sides by x minus 1. So we write x minus 1 over 1 here because we've got a fraction going on, a rational expression. And write an x minus 1 on this side. This side multiplies out to 0. This side just gives us 2x minus 5 equals 0. And we solve that, and we get x equals 5 halves. Okay. We can put those points in a graph. Here's 5 halves 0. And here is 0, 5. Now there's more, and I've written down more. At least one student wanted to do long division here. Now, we don't ordinarily do that. We were introducing this, and probably a mistake we've done it, but we did it, so we're going to do it. Okay. We divide x plus 1 into 2x minus 5, and actually it's x minus 1. And if we divide x minus 1, of course, we're going to get a minus 2 here, which kind of make that a plus. And we make this negative 3. Then pause and clean up the board just a little. Okay. Anyhow, when we do this division, here's the quotient we end up with. Okay. What I made is that the other thing we want to do in doing this graph, so we want to do the long run behavior. If that goes toward infinity or negative infinity, if that's approaching infinity or negative infinity, what happens to this quotient? Well, if x approaches infinity, your denominator is going to approach infinity. When you divide something that approaches infinity into something that doesn't, you're going to get 0. Okay, or you're going to get something that approaches 0. So this approaches 0, both for x approaching infinity and negative infinity, leaving you just a 2. So as x approaches infinity, y is going to approach this horizontal line, y equals 2. The graph is going to approach the horizontal line. Now, the graph of negative 3 over x plus 1, and I went through some detail on this, but I have the wrong function. I was going to say it's a vertical stretch of the 1 over x function. So the 1 over x function kind of looks like this, where you got the point 1, 1 here. I don't have a good place to label that. If this is the 0.11, then if we do a vertical stretch by factor 3, that point's going to go up to 3.1. And the graph is going to stretch by factor 3 in this direction. So it might end up looking something like this. And same thing's going to happen down here. Instead of this point, we'll have a point about 3 times as far. And the x-axis is going to look like this. If we then reflect it about the x-axis, it's going to go down here. So it's just going to turn upside down, and we're going to have a graph that looks like this. And this. So we can kind of clear these out. Say that, okay, there's our graph stretched by factor 3, reflected about the x-axis. Then we have to shift every point 1 unit to the right. And that should be a minus there. Okay. Because x in the 1 over x function to be replaced by x minus 1. And that takes every point and shifts it 1 unit. Now, 1 unit, right there's 1 unit. So shifting right 1 unit shifts every point 1 unit to the right. Give something like this. As the graph approaches the y-axis, the curve is going to approach the line x equals 1. And then we do the same thing here. We shift every point 1 unit to the right. The graph is going to approach the line x equals 1. So it's like we've got a graph that approaches y equals 2 near the line where x equals 1. Got a vertical asymptote. And it's going to look like this and like this. And well, on this side, it's going to come through the x-axis at some point. So it's going to do something very much like this. On this side, now you still have the effect of the 2x minus 5. It's like 2 plus this. So I can take this thing and it's as if at some point we start raising this thing a couple of units. And I'm being a little vague about that because that's a little more complicated than we're going to make it. But we end up with an asymptote at y equals 2, and that's what the graph is going to look like. Okay. As x approaches infinity, y approaches 2. As x approaches negative infinity, y approaches 2. As x approaches 1, y approaches infinity or negative infinity. Okay. And that happens. Now, let's translate this into a method. When we have a function like this, and this is a polynomial divided by a polynomial. Polynomial degree 1, it's just a linear function divided by a linear function. It's the simplest, about the simplest example we can get. Okay, we find the y-intercept. Then we get zero, 5. Find the zeros of the numerator, and we get x equals 5 halves We get the 0.5 half zero. We've already done that. We understand that. We understood that when we started. We find the zeros in the denominator. X minus 1 equals 0, so X equals 1. Now, there are other cases. In this case, without going into more detailed explanation, we can get pre-calculus class. Here is the denominator applied a vertical asymptote. And in this case, acts like a transformed 1 over X because you got something over X minus 1. And I'm going to state that a little differently. You'll say it acts like a multiple. Of 1 over X minus 1. And we recognize 1 over X minus 1 as being a horizontally shifted basic reciprocal function. Tilted reciprocal function. Now, a multiple of that is going to be vertically stretched or compressed and maybe reflected. And that's an explanation of why you do get a vertical asymptote. It acts like 1 over X minus 1, understanding the behavior of the basic reciprocal function. Again, we see this is simply horizontally shifting basic reciprocal functions. So we shift the basic reciprocal function over to at where the asymptotes at X equals 1. And then we multiply it by whatever 2X minus 5 is when X equals 1. Well, it turns out that's negative 1. Okay, so that's what happens when we graph. We do this. 0.05 on the graph. Put 5 half 0 here. And we do X equals 1. That down here. We have vertical asymptotes at X equals 1 because the function acts like a multiple of 1 over X minus 1. So we write, well, we sketch vertical line X equals 1. Also, you can do the long division. You're going to get 2. Okay. The large values of x, it just acts like 2x over, not over 2 over x. So we get a horizontal asymptote. And y equals 2. Now, how are we going to get through the x-axis here? Through the vertical asymptote at x equals 1 and a horizontal asymptote at y equals 2. Well, we're going to just do this. As we did before with a lot more explanation, this is what it comes down to. And then over here, you got to go through this point with the vertical asymptote here and a horizontal asymptote here. There it is. So there's our graph. Now look at a couple more examples following the same procedure because they can get a little more complicated. Okay. When we do this, we find the y-intercept. We find the y-intercept. The y-intercept occurs when x equals 0, so you get y equals 0 minus 2 times 3 times 0 plus 9 over 0 plus 1, which is negative 18. That's what gives a point in the graph. X is 0, y is negative 18. There's the y-intercept. The x-intercept occurs y equals 0. So you get x minus 2 times 3x plus 9 over x plus 1 equals 0. Multiply by x plus 1. And we see that the x plus 1 and the 1 can switch places. We end up with a 1 here. So we just have x minus 2 times 3x plus 9 equals 0. So x minus 2 equals 0. Or 3x plus 9 equals 0. This is basic principle used grabbing polynomials, which you're going to have to do in the test. Okay. If a product of things is 0, then any one of those things could be 0, and that would make the whole thing 0. So x minus 2 could be 0, meaning that if x equals 2, you're going to get 0. And you can plug that back in. If you plug in x equals 2, you're going to get 2 minus 2. That's 0. Now this is going to be 15, but 0 times whatever this is, whether it's 15 or 98 or even 0, it's going to get you 0. And 3x plus 9 equals 0, that's easy to solve. Everybody can solve that. You get x equals negative 3. So if you plug in x equals negative 3, you get negative 9 plus 9 is 0. Okay, and the whole thing is 0. Now you got to find the zeros of the denominator, and what does that mean? So go ahead and find the zeros of the denominator and see then what you know about the graph. Okay, now I got to say, you really need to focus on every step without thinking about anything else. Okay, focus on this step. Don't worry about what the graph's going to look like because you don't have a clue at this point. Now, once you get some experience with these, you know you're going to get, you have an idea what the graph might look like. Okay, but find the y-intercept, that's one step. Okay, everybody did that. Find the x-intercepts. Or the zeros of the numerator. Okay. And I've been a little ambiguous. I could have said find the x-intercept. Well, those would be the zeros of the numerator. Then find the zeros of the denominator. Okay. Do this, do this. Identify the denominator, find the zeros. Then we're going to go over and do something with the zeros of the denominator. But first we're going to find them. Then we're going to think, okay, here's what I do with the zeros of the denominator. If you're worried about what the graph's going to look like at this point, then you're confusing yourself. Okay. Now, eventually, after you do a few of these, you'll have an idea where it's headed. But you don't worry about what the graph's going to look like. You find the zeros of the denominator and you do what's necessary with those. Keep it as simple as possible, one step at a time, one simple step at a time. Okay, zeros of the denominator. Denominator is x plus 1, that's set equal to 0. And you can solve that real quickly. Now I write out the step. I know you can solve this and get x equals -1 in your head. And you can identify the denominator 0 when x equals -1. But you're going to have more complicated denominators. And you want to write out denominator equals 0. You want to write out the equation and solve it. Just like we wrote out the equation for the numerator equals 0. Here, that came out of the y equals 0 idea. And we write out this equation. We don't just look at this expression and say, okay, they're going to be our zeros. Write out the equation. Okay. Write out all the details and get in the habit of writing all the details. And then things will become clear to you and you won't get confused. Because this is confusing. It's one of the hardest things that people encounter in a pre-calculus course. People very successful in my pre-calculus course in the home. They screwed this up right and left. Okay, they did everything else. They screwed this up. Couldn't get this. Okay, so I know it's tough. That's why I'm giving you step by step and telling you to focus on the steps. Okay, well, now that you've done this, you have information. Also, the long run. Now, Open Math is going to tell you a little bit more about long run. We could expand the numerator and do a long division. We get an x squared in the numerator, which means we do get the long division, we'll get an x plus something. Okay, well, we could think that through, and if you're good with long division, it's fine to kind of do that in your head, but numerator is 3x squared plus a bunch of stuff if we multiply it out. We don't need to multiply it out to see. We don't need to multiply the whole thing out. We don't need to expand the whole numerator to see that we're going to get a 3x squared. The denominator is an x plus something. And if we divide the highest power term in the numerator by the highest power term in the denominator, this is what we get, and that's 3x. So we do this. Program behavior can be a little bit complicated. But it comes down to this, and you'll see more of that in the pre-calculus class. The next step, you actually do this in 2 steps. You put the information you have on a graph. You put the x-intercept and the y-intercept. Okay, we've got 2 x-intercepts. X equals 2. And x equals -3. We have the y-intercept at 0, -18. We have the vertical asymptote. It x equals -1. So let's say here's x equals -1. And the graph also approaches y equals 3x. I just told you something wrong. In this case, we do have to do a long division. And we do a long division, x plus 1 into 3x squared plus 3x minus 18. We get 3x. And that's not all we get. We get 3x squared plus 3x. Actually, turns out what I told you appears to be true. It's by accident. So the graph approaches 3x. Now, if this hadn't matched this, then we could get a 3x plus a number. In this case, well, the graph actually approaches 3x. So here's, let's say y equals 3x. That's not very accurate. We should have less slope than that, but there it is. Okay, so here's what we know about the graph. Now we're going to have vertical asymptote at x equals -1. We've got to go through these 3 points. We've got to approach this line as an asymptote. So it's going to look something like this. Do all that step by step. We put this stuff on the graph before we try to draw a curve. And we don't even attempt to draw the curve until we get all the information on the graph. Don't think ahead of what the curve is going to look like. You probably don't have a clue. Many times, if it's complicated enough, I don't have a clue until I get all the information on the graph. Okay? So please, one step at a time. Okay, so we're going to graph this thing. Now we know that when we graph anything, the first thing we want to do is find the axis intercepts. I mean, there are other things we could do first, but that's what we've gotten used to doing. So the axis intercepts. So I'm going to write down y-intercept, and then in parentheses, x equals 0, because we know that the y-intercept occurs when x equals 0. And the x-intercept is going to occur when y equals 0. X-intercept will occur when y equals 0. Okay. Now, if x equals 0, we're going to get this, and it's important to write out this step. It's important to write out these words. If you write them out, you reinforce the idea. And everybody at this stage needs to keep reinforcing these ideas. Well, if we multiply this out, that's going to be -3 times 2 times -1 over 3, which equals +2. Okay. Now, that gives us information that we can put on the graph. And it doesn't hurt anything to start putting our information on the graph. Let's go ahead. Well, let's find the x-intercept before we do anything else. Because we have to know how to scale the graph. We know that our y-scale has to go up at least 2. What's our scale going to be like for the x-intercept? Well, y equals 0, so that this, okay? We solve this equation. We multiply by 2x plus 3. And we get this equation. Right? Now, I did that in detail before. This we multiply by 2x plus 3. We're going to have like 2x plus 3 over 1 times this. 2x plus 3 and the 1 can switch places. So we have 2x plus 3 over 2x plus 3 gives us 1 and so forth. But we can't multiply by 0. So 2x plus 3 can't be 0. And 2x plus 3 is 0 if x is -3/2. So that's why we put x not equal to -3/2. That step usually doesn't make any difference, but sometimes it does, and it's a good idea to remember to do it. I'm not going to emphasize it right now, but we will encounter it later. And so remember, it's a good idea to do that. Okay. Well, this means that zero property multiplication. These things are all multiplied. If any one of them is 0, we get 0. Have to understand that. Okay, so x minus 3 could be 0, x plus 2 could be 0, x minus 1 could be 0. I recommend that you write out that step. Because sometimes you have more complicated expressions. And if you're used to writing out this step, you're not going to mess up those more complicated expressions. You're less likely to mess it up. If you try hard enough, you'd be like me and mess all kinds of stuff up. Okay, x minus 3 equals 0. Solve that. We get x equals 3. or x equals -2, or x equals 1. Now, we have some information that we can put on the graph. We don't want to draw a curve or anything because we haven't finished in our information. We haven't looked at the long run behavior. We haven't looked at the fact that the denominator could be 0, and that has a big effect on the graph. So we don't want to try to even think about what the curve's going to look like. We write down our information. Okay, so probably a good idea to find the zeros of the denominator as well before we write down all our information. So I'm gonna wait till we do that. Okay, so zero or zeros of the denominator. Well, we set the denominator equal to 0. We see that occurs when x equals -3/2. Okay, so what are we going to do with this information? Now we know that the most important behaviors occur between x equals -3/2 and x equals 3. Because all the rest of the numbers are, but not sorry, between x equals -2 and x equals 3. And our y-intercept is at 2. We want to leave ourselves a little room, but I'm going to put -3 about here. -2 about here, 3 about here. So I'm going to set up a scale. I'm going to put -4 here. Should have been a little further to the right, but here's the. Closer. Okay, this distance and this distance are equal. Then I can divide, I like 4, I like to use powers of 2. Okay, divide this in half, I get 2. Divide this in half, I get 2. Divide this in half, there's 1. There's -1, there's -3, and there's 3. We know what these numbers mean. And then on the y-axis, I'll put 2. And that'll be the point 2, 0. Right, figure out what I need to label that. I'm going to label it kind of lightly. It's not 2, 0, it's 0, 2. There it is. Okay, now our x-intercepts, we know that the points 3, 0, -2, 0, and 1, 0 are on the graph. So here's 1, 0. Here's 3, 0. And here's -2, 0. I'm not going to label them, but it doesn't hurt to label them at least lightly. Because you're going to be drawing curves and you don't know if your curve is going to go through any of your labeling at this point. Okay. But there's a lot of information. What are we going to do about the 0 of the denominator? Well, as I explained in more detail in the earlier part of the video in the support class, if the denominator is 0, you don't have any y value. The function is undefined because division by 0 is undefined. If the denominator is close to 0, then it's going to be really, and the denominator is going, well, yeah, if the denominator is close to 0, it's going to be really tiny. And if the numerator isn't really tiny, you're going to get a really big number. Okay, small denominator gives you a big result, unless you're dividing it into something that's also small. So, what do we do with the 0 of the denominator? Okay, denominator near zero implies a big, I'll say absolute value of y value. Unless the numerator is also near zero, which means that you're going to get great big positive or great big negative y values when x gets close to -3/2. Well, where's -3/2? Here's -3/2. Sorry, yeah, -3/2 between -1 and -2. And that's going to be a vertical asymptote. Oh boy. The way to fix that. It's like 1/x when you approach the y-axis. Okay, well, it's like this and like this. 1/x squared would be like this. And of course, they could be upside down because you could have negatives. You'll see that in a minute. Okay, so we have a graph that has to go through all of these points and has to be an asymptote with it to this line. So you've got to approach this line as a vertical asymptote. Next thing we have to think about is the long run behavior. I'm just looking to see if I can find room to do it. Well, okay, long run. We just think in terms of numbers. I'll figure out how to write it out in a minute. If X is really big and positive, what can you say about the value of Y? Well, it's like if X is 1,000,000, then this number is going to be close to 1,000,000, this number is going to be close to 1,000,000, and this number is going to be close to 1,000,000. So you got like 1,000,000 times 1,000,000 times 1,000,000. Okay. What's this number close to? It'll be close to 2,000,000, isn't it? Okay, I've got 1,000,000 times 1,000,000 times 1,000,000 divided by 2,000,000. Well, divide this 1,000,000 by 2,000,000, you get 1/2, right? You still have this 1,000,000 and this 1,000,000 left. And 1,000,000 times 1,000,000 is really big. It's 1,000,000,000,000. Okay. Count to 1,000,000. Takes you about a month. You do it full time. Bother to sleep and eat sometimes. Okay. Rest of your days to spend time. Take you about a month. Okay. Count 1,000,000 times 1,000,000. Well, you count 1,000,000. The month's over, you think, boy, I got that done. Oh man, now I got to do that 1,000,000 more times. 1,000,000 months. Okay. Well, 1,000,000 months is almost 100,000 years. See a couple of ice ages by then. And you're not going to live it. Okay, 1,000,000 times 1,000,000 is really big. You count all day, every day. 100,000 years, which would be 1,000 long lifetimes. If you can start counting when you're 3 years old, finish when you're 103. Okay. Big number. So if X is a positive 1,000,000, then you're going to get a positive huge number. So we can say as X goes to infinity, Y goes to infinity. That just doesn't go to infinity, it goes infinity really fast. And then well, if x goes to negative infinity, it's like you got a negative million, negative million, negative million over negative 2 million. Is that going to be positive or negative? Well, you've got 4 negatives multiplied and divided. Any two of them can be paired up and make it positive, so you get all positive, okay? And I'm not gonna wave my hands and explain that. It's pretty clear that if you got negative, 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 and negative, that's a positive. Y goes to infinity. So now we can sketch a graph. Graph's got to go up here. It's got to go up here. And then it's got to go through this point, this point, this point, and this point. It's got to be an asymptote with this line. What's it going to look like? Well, it's going to come down from here. We go through here, and then it's going to be an asymptote down here. Has to be an asymptote with this beneath the x-axis for negative values of y, because it has to start up here and go through this point. It goes through this point, it can't get back up except by turning around, and it's got an asymptote there. Doesn't turn around, just approaches the asymptote. Okay, on this side, it's got to have an asymptote here. Now, is the asymptote up or down? Well, since this thing's linear, it's going to be opposite to what this is. I'm not going to get into that right now. I'm just going to say, well, if it's down, then it's got to go from here and get to here. If it starts as an asymptote for negative y, it's got to go through the x-axis to get to this point, and it can't go through the x-axis. Because the only place it can go through the x-axis is at one of these 3 points. Okay, there's no point here where it can go through the x-axis. It's definitely not 0 at any point between here and here. Because the only place, if x isn't one of these 3 numbers, 3, negative 2, or 1, then this isn't 0. None of these are 0, except at those values. So it can't start down here, so it has to start up here. It starts up here, it's got to go through this point, and then this point, and then it's going to go through this point. So it's going to have to turn around, come back through this point, and so it's going to do something like maybe this. Then come on. Not sure that's got the right shape. We can analyze shapes in much more detail once we learn a little bit of calculus. But this is pre-calculus. We're not going to even touch that. It's not one of the more difficult things you do in calculus. It's not too hard to figure out more about the shape. Like, where is this point? Does the concavity change and stuff like that? In this course, you kind of learn what all that means, but you don't learn how to do it. So there it is. That's the process applied to this graph. Now I'm going to say a little bit more. If I expand the numerator, if I multiply x plus 2 by x minus 1, I get x squared plus x minus 2. If I multiply that by x minus 3, I'm going to write out all the steps of the distributive law. And I want to do this quick. I'm going to do this because I want you to understand that you need to do it too, so you don't make any mistakes. You're less likely to make mistakes. Okay, so there's the distributive law applied to this product, and that gives us x cubed plus x squared minus 2x minus 3x squared minus 3x plus 6. And that equals x cubed minus 2x squared minus 5x plus 6. So y equals x minus 3 times x plus 2 times x minus 1 over 2x plus 3 equals x cubed minus 2x squared minus 5x plus 6 over 2x plus 3. What's that equal? Well, we can divide that. Okay, divide this into them. We get 2x squared. Sorry. We get 1/2 x squared. Which I'll write as x squared over 2. We multiply x squared over 2 by 2x, we get x cubed minus 3/2 x squared. And we put a fraction in there. That wasn't a good idea. And we make sure we get our signs right. And we get 1/2 x squared minus 5x, which means we're going to get x over 4. And that's going to give us 1/2 x squared minus 3/4 x. And we minus here and plus here. 5 3/4 is 23/4. And finishing it out, we're going to have 23/8. And I'll try to do that in my head. You get 69 over 8. Subtracted from 6 leaves me 3/8. I think. Question mark on a lot of this. Okay, now. My purpose isn't to illustrate long division. But if this is correct. And I did some of it might have. If this is correct. We get y equals this. This, when x gets big, approaches 0. This is a quadratic function you could graph. You can find its vertex, you can find its intersects. Okay, this stuff you're going to have to do in a test. Okay. So there it is. Which means that in the long run, your negative B over 2A is going to be, I think, -1. Negative B 1/4. No, so 1/4. Well, anyhow, I don't want to think of the discriminant. Okay. This thing is like a parabola. And that parabola represents this much of the function. Then we add this function, which is just a transformation of the 1/x function. Shifted left 1.5 units, 24/16, 1.5. You don't have to know the details of that, but that agrees perfectly with the fact that we have a vertical asymptote at -1.5. Okay, so this function has a vertical asymptote that actually was -3/2. So what's going to happen is we've got something very much like the reciprocal function, but with the vertical asymptote here instead of at the y-axis. When you get close to this line, this vertical asymptote overwhelms this parabola. So we got a parabola. The vertical asymptote dominates in the vicinity of x equals -3/2. Okay. The parabola dominates when you get far away from it. Now, when you see what you're going to get might well end up looking like this. When you're out here, the y values down here are small, so this kind of wins. When you're out here, this thing gets real small, so this thing kind of wins. Kind of different coloring here. So, follow pretty close to this curve here and here, because the values of this red function are pretty small. But now between here and here, the values of the red function start getting big. So now we've got to start following the red function, and it gives us something like this. Then over here, we've got to follow the red function. And the parabola is going to kind of pull it down. They're going to have something like this. So when the red function wins, we have all this stuff going on. Everywhere else, we just got this blue function. Now, if you understand that even a little bit, makes a little more sense of the idea that the long run behavior is governed by the leading term of the numerator and the denominator. So your function, if we expand it, has an x cubed out in front. We don't have to go to all the detail of multiplying this by this by this to understand that when we do, we're going to get an x squared when we multiply these two. And then we multiply with this, we get another x. We're going to get an x cubed when we expand this. Just think about what you have to do to expand it. Every time you multiply by the term with an x in it, you're going to get a higher power of x. So you multiply this by this, you're going to have an x squared plus something. In this case, x squared plus x minus 2. When you multiply that by the x minus 3, you're going to get an x cubed. When you're looking at the long run behavior, we don't worry about the rest of it. Okay. Y approaches 1/2 x squared as x approaches infinity. So the graph pretty much is acts like the graph of 1/2 x squared. Just like you got this parabola here, goes up on this side, up on this side. As y goes to infinity, 1/2 x squared goes to plus infinity. As y goes to negative infinity, 1/2 x squared goes to plus infinity. Okay. So as you'll see, when you do the problems, look at some of the videos. Ultimately, it's the leading coefficient of the numerator and the leading coefficient of the denominator that determine the long run behavior. Okay, leading term of the numerator and leading term of the denominator. And what I mean by leading term, I mean the highest power in the numerator and the highest power in the denominator. Divide the highest power by the highest power. You see whether you have an even function or an odd function. Okay, and you see what happens at infinity. So I want you to understand that, so you know that you need to do this. I'm never going to ask you to expand the thing and do the long division. But by looking at what happens when you expand and do the long division, you get a better understanding of why you have an asymptote and why you have the long run behavior. Again, this remainder term gives us the asymptote. And this polynomial here gives us the long run. Okay, so this is a lot of fun, right? So let's have more fun. Let's do another one. How much of that process we can do right out? You know, we're doing the y-intercept. Stop and write this out. Write this out. Write this out. Imitate what I've done here as closely as you can. Of course, you're going to have a different function. It might work out differently. Okay. Okay, just a little simpler. But there's a twist in it that nobody's seen yet. Not much of a twist. Just follow the procedure and take what you get and see what happens. Okay, here we have rational function of this road is y equals x plus 7 over x plus 2 times x minus 3. I'm still not seeing people writing this out. I want to see these very words every time you find a y-intercept, okay? I want you to have it so that you can look back at your work 3 days later, try to review for test, for example, 3 weeks later, and understand just what follows. You don't write out a bunch of calculations. You don't write out just the coordinates of a point, even if it might be obvious. Okay, so let's write this out. Then you let x equals 0. Can you find that y equals -7 over 6? And I would write out, so your y-intercept is at 0, -7 over 6. You put words in here to keep yourself straight and to help yourself identify errors if you get to the end of this problem and nothing makes sense, okay? And that's possible if you make an error. You can have a graph with characteristics that just aren't going to work. So you have to be able to go back and fix it quickly. That's the x-intercept. X-intercepts occur when y equals 0. So you have this. Okay. Well, again, multiply both sides by the denominator, and you get x plus 7 with 3 dots here, ellipses. You get x plus 7 equals 0. But x can't be -2 or 3 because that would make your denominator 0. And you can't multiply by 0 and all that stuff. You get x equals -7. They say, well, we call it then that -7 0 is the only x-intercept. Them zeros in the denominator. X plus 2 times x minus 3 is 0. Are you going to get 0? Well, if x is 3, you're going to get 0. If x is -2, you're going to get 0. This splits into 2 equations, x plus 2 equals 0, or x minus 3 equals 0, because if you multiply 2 or more things together, you get 0. One of those things has to be 0. Any one. Could be this one or that one or that one. Okay, so x equals -2. where X equals to 3. We have vertical asymptotes at X equals -2 or X equals 3. Your long run behaviors like y equals highest power term of the numerator over highest power term of the denominator, assuming numerator and denominator are both expanded. So the long run is like 1 over x. So you find that y goes to 0 as x goes infinity or negative infinity. And that's what 1 over x does. If you divide 1 by a big number, you get something close to 0. We'll put that on the graph. Put all this information on a graph. Our only x-intercept is at 0, 7. Our y-intercept is at -7 over 6. And let's see our asymptote. There's a point 0, -7 over 6. And we have vertical asymptotes at x equals 3. And at y equals -2. X equals -2. Long run behavior. We approach y equals 0, which means we approach the x-axis. So all right. There's horizontal arrows here indicating an approach to the x-axis. Now, can you draw me a graph that has those characteristics? Okay, this is tricky. The only place we go through the x-axis is here. We got to have asymptotes here and here. And we got to approach the x-axis over here. Now, how are we going to approach the x-axis over here and have an asymptote here? Well, it means we've either got to do this or this. Right? The x-axis and this line have to be asymptotes. We don't know yet which one to do, although we can figure it out. And it's going to turn out to be this one, but actually can't be. What a problem here. Okay. X is negative here. And it can't cross the x-axis between here and here, because the only place you can cross the x-axis is at 0, 7. So it's gotta be. Okay. Gonna come up. Through this point. And then back down. There's an asymptote here and here. Okay, now, if x is bigger than 3. Oh, boy. Notice my solution here was x equals -7. Not only did I label that backwards, even though I said -7, 0 is the only x-intercept. Turned it around and I put it in positive axis. I lost the negative sign. Just be very careless. I apologize for that. Okay, we have -7, 0. Now the graph's gonna work. I'll explain how I knew it could be like this. Doesn't have to be odd here with this. All right, so what happens is we come along here below the x-axis. We dip down and then we go up to the vertical asymptote here. And now over here, if x is bigger than 3, all those numbers are positive. So this is going to be like so. All right, so there's what your graph looks like. Now, there are a lot of different cases, a lot of different ways these can act. We ran into a bunch of problems because, not everybody's getting the 0 property, and there's just a lot of algebra errors. So we want to really pay attention, make sure we get those out of our system. So you're going to see a lot more detail on some of the things you do, but this should give you a foundation for understanding what you see in your open math. Okay. Now, I just printed off some copies for you, and I'm going to run over and pick those up. If you have a couple of minutes to stick around, I should be back within 3 or 4 minutes. If you don't, I'll put some copies in the testing center. And you can go in there and ask for copies.